China has filed a plan at the United Nations to build a permanent base on Mars. Not in theory, not eventually, by 2038. And the plan doesn't start with sending astronauts. It starts with something else. So how do you build a base on another planet without sending any astronauts? The answer has three phases. Phase 1 kicks off in 2028 with a mission called Tianwen-3. It will drill 2 meters into the Martian soil, deeper than any successful Mars drill in history. It will hunt for water ice and test prototype robots. This phase determines if the ground is stable enough to build on. If the data comes back green, they move to the next level. Phase 2, starting around 2038, is the robotic build phase. A 10-year window where machines work 24/7 in the freezing Martian dark, manufacturing air, water and power. Finally, once everything is ready, Phase 3, human arrival around 2050. China calls this the inheritance model. Humans don't arrive as exhausted builders, they arrive as heirs, stepping off the ship to inherit a planet that's already working. But at this point you might be thinking, why not just send humans in the first place? It comes down to capability and cost. Sending anything to Mars costs $100,000 per kilogram. That's why Mars has to provide everything humans need, and to make that happen, machines have to be there first. But building from scratch on a world no human has ever touched requires more than just a plan. It requires the perfect location. And that's where the 2028 survey becomes make or break. Right now, China is evaluating dozens of candidate landing sites on Mars. But out of all of them, only 3 locations are strong enough candidates for what comes next. Choosing a site on Mars isn't like picking a spot for a tent. The requirements are brutal. You need flat terrain so the robots don't tip over during construction. You need the right altitude so the atmosphere is just thick enough for a safe landing. And most critically, you need to be sitting directly above underground water ice. Without it, there's no oxygen, no rocket fuel, and no base, full stop. That's exactly what Tianwen-3 is going there to confirm. When it lands in 2028, it will measure whether the ice is actually there, how deep it sits, and whether the ground above it is stable enough to build on. If the answer is no, the 2038 robotic base doesn't happen. And that's not all. Tianwen-3 also carries a 6-legged robot and a small helicopter. They're prototypes for the machines that will eventually build the base, and their purpose is to figure out if they can survive on their own. Because here's a problem with operating anything on Mars. There's a 20-minute communication delay between Earth and Mars. One way. That means if a robot gets stuck, Earth won't even know about it for 20 minutes, and sending instructions back takes another 20. A 40-minute round trip for a single command. In a construction environment, that's huge. So these machines can't wait for instructions. They have to detect problems, make decisions, and fix things entirely on their own. Everything depends on what that drill finds in 2028. And if the results come back positive, the real construction begins, with materials nobody expected. Because here's something most people don't know about Martian dust. It might actually be stronger than steel. Now let's say this survey goes well. What happens next? There will be 4 types of robots. Excavators handle the hard physical work, digging foundations, mining underground water ice, drilling pits for the nuclear units. 3D printers take raw Martian soil, process it, and print structural elements layer by layer. Assemblers install the interior systems, sealing airtight doors, connecting power cables, placing components with robotic precision. Logistics bots run the continuous material chain from mining to printing to assembly. Before any of them leave Earth, they train in VR. Engineers create a digital twin of the landing site using Tianwen-3 data. Inside that simulation, the robots practice the build millions of times. By the time they touch down, they already know every rock, every slope, every measurement. Components arrive barcoded for millimeter-precise placement. If one robot fails, the others detect it and adjust automatically. The base builds itself. But even the most advanced robots are useless without one critical thing. If this base is going to survive freezing Martian nights and months-long dust storms, it needs an energy system that never goes down. The very first thing robots do when they touch down isn't drill and it isn't build. It's set up solar panels. That makes sense. Solar panels are lightweight, foldable, and Mars does receive sunlight, about 43% of what Earth gets on a clear day. For the early weeks of operation, they're the logical starting point. But Mars has a problem that no solar array can solve on its own: dust storms. In 2018, a planet-wide storm wrapped around Mars and blocked sunlight for months. NASA's Opportunity rover, which had been operating for 15 years, went dark. Its batteries never recovered. For a robotic construction base that needs to run non-stop for a decade, that's an unacceptable risk. So China's plan doesn't rely on solar alone. The base includes a compact nuclear fission reactor. The two systems complement each other. Solar panels carry the load during clear periods. The reactor keeps running when dust storms hit. But power is only half the problem. Even with the lights on and the heat running, the base is sitting on a planet with no breathable air, no drinkable water, and no fuel to get anyone home. That's the next challenge. The solution is a factory designed to live off the land, converting what Mars already has into what humans will need. It runs on two things Mars has in abundance: its atmosphere, which is 95% carbon dioxide, and the water ice the excavators mine from underground. Here's how it works. First, robots compress carbon dioxide from the atmosphere and mix it with hydrogen extracted from ice inside a heated reactor. The Sabatier reaction produces two things: methane gas for rocket fuel and water as a byproduct. Next, an electric current splits that water back into hydrogen and oxygen. The hydrogen gets recycled into the first step to make more fuel, while the oxygen is chilled and stored. By the time humans land in 2050, the base will have stockpiled thousands of tons of methane and liquid oxygen. The complete return launch package, processed and waiting. So back to that question from earlier. How is Martian dust stronger than steel? Researchers found that if you melt Martian regolith at around 1,500 degrees Celsius and pull it into thin fibers, you get a material with a tensile strength of 1,320 MPa. That's roughly 3 times stronger than the structural steel used in standard construction. The dust Mars has been burying our rovers in for decades turns out to be one of the strongest building materials in the solar system. The robots will use these fibers to reinforce sulfur concrete. They take sulfur, abundant in Martian soil, melt it at a low 140 degrees Celsius, mix it with raw regolith, and pour it. This Marscrete doesn't need a single drop of water to cure. It sets in just a few hours and gets stronger in the Martian cold. It's still being tested under near-vacuum conditions, but early results suggest it could be the most practical structural material available anywhere on Mars. The final base would be shredded by radiation and micrometeorites in weeks. Instead, it'll look like a series of artificial mountains. The walls will be meters thick to block cosmic rays. Inside, there will be flexible modules that the robots wrap in thick shells of Marscrete to keep the warmth in and the vacuum out. No human hand will touch these walls until they're finished. The base assembles itself, modular, shielded, and ready to grow. Now, if we have all the required stuff, then what's stopping us from starting tomorrow? Mars. Mars is what's stopping us. Mars is trying to destroy these machines every single second. Right now, 3 major engineering problems haven't been fully solved. Challenge 1 is the deep freeze. The average temperature on Mars is around -80 degrees Fahrenheit. At that level of cold, normal Earth grease freezes. Electronics crack under stress as temperatures change from day to night. That means every motor, gear, or joint on these robots has to be redesigned in a way that they can endure such temperatures. Challenge 2: the water ice gamble. We already know water ice exists on Mars. Orbiters have confirmed it. The real question is whether it's accessible enough to mine at an industrial scale. Even with confirmed ice presence, the real question is depth and hardness. If it sits too deep to drill at industrial scale, the production chain breaks. You could have the best robots ever built and still run out of the one raw material everything else depends on. But the hardest challenge isn't the cold, and it isn't even the ice. It's what happens when something goes wrong. If a robotic arm jams mid-task, a bolt strips, a 3D printer clogs at a critical layer, the autonomous system has one shot to solve it with whatever tools and materials are still functional. No replacement parts, no human override. And here's the risk. We're testing this failure recovery capability for the first time at industrial scale on another planet with a decade-long construction timeline riding on it. Now fast forward to the year 2048. For the first time in 3 billion years, Mars is alive. The lights are on, corridors are pressurized. Deep inside the base, sensors quietly monitor oxygen levels that have been rising for years. The robots are still there, but they're not building anymore. Now they patrol the halls, clean dust off equipment, and check the fuel tanks. For 10 long years, there hasn't been a single human heartbeat on this planet. No one has breathed this air. No one has walked these floors. But the base is breathing for us. It's warm, it's stocked, and it's waiting. Then comes the year 2050, the moment the history books will talk about forever. When the first human ships arrive at the landing site, it won't feel like the Apollo missions. These astronauts won't have to rush to survive their first night. They won't be racing against time to set up life support before their oxygen runs out. They simply walk to the airlock, open the door, flip a switch, and the lights stay on. The machines become quiet protectors of the humans they were built to wait for. This is the shift China is betting on in the new space race. You don't conquer Mars by planting a flag. You prepare it first. You make it livable before the people even leave Earth. If China succeeds, the Red Planet will become a blueprint. The challenge isn't just reaching Mars, it's learning to build there. And whoever figures out how to build without importing materials will rewrite what's possible. This Mars logic has massive implications back on Earth. The same systems 3D printing habitats from Martian dust could build sustainable housing in remote deserts, research stations in deep oceans, or disaster relief shelters where roads no longer exist. We're moving toward a future where construction doesn't require supply chains, just raw materials and machines smart enough to use them. The 2028 drill is being prepped for launch. China is attempting to build the first off-world facility that doesn't need Earth to survive. The only question left is, once the machines finish building, are we ready to move in? What do you think? Is the inheritance model the right way to settle Mars, or is autonomous construction too big a gamble? Let us know in the comments. And if you want to see more breakdowns of the world's most ambitious engineering projects, subscribe to Megabuilds. Thanks for watching.